So, good morning, everyone. Um, I hope everyone can hear me properly. My name is Thomas, and it's a pleasure for me to be here, especially as I was one of the first PhD students of Nanocem, starting to work in the consortium about 10 years ago. During the next 30 minutes or so, I'd like to give you a bit I'll take you on a journey in time. And the presentation I gave you is called Thermodynamics from Phase Diagrams to Predictive Engineering. I've on purpose chosen the title From Phase Diagrams to Predictive Engineering because I think it gives you also a feeling for scale, because we're starting off with small scale and I want to finish with, say, big scale as we're doing, as we're used to do it in industry, etc. I scheduled my talk as follows. I will start with some of the results of Core Project 1, which is the impact of limestone on cement hydration. Quite a few people have probably heard about this, but I thought it would be a good opportunity at a 10 years meeting to come back to this and also show you how things were evolving in the last 10 years. I'll continue with some of the work that's been elaborated in the Transcend program. Karen was quickly introducing it, and we had the pleasure to have an industrial doctorate student in Holcim then. And finally, I'll finish off with some of the more application side of the thermodynamics, and really want to show that there's also links between thermodynamics and civil engineering. They're more on the applied side, but nevertheless, they're very important links. Anyhow, before I really come to the technical details, I'd like to really step back 10 years, and it was I think it was a very nice April day here in Lausanne. I met Fred and Barbara, and they offered me this PhD studentship, and it was really nice. And I said, okay, well, I'll come to Aberdeen. And I've never been there before. And it was on the 10th of August in 2004. I was on a ferry and shipped in Zeebrugge in Belgium. I had a beautiful sunset. I enjoyed the beer and was looking very much forward to go to Scotland. So I went to bed. The next morning I woke up. What I basically thought I was arriving at the end of the world. There was virtually rain everywhere. My car broke down. And apparently it was a really bad summer because even there was papers published about this tremendous weather event in August 2004. So finally I managed to arrive in Aberdeen, and I thought, oh my gosh, I'm not going to survive a week here. But luckily I found such nice people such as Fred and Donald there, and they showed me that there's life is possible in Aberdeen. You can survive for quite some time, then you can even do nice things. And they showed me, okay, well, Thomas, in your PhD studentship, we want to work on thermodynamics. Why do we want to work on thermodynamics? Coming back to the technical things, thermodynamics is a very generic approach. With thermodynamic calculations, you can do a lot of things. You can basically master the science of very complex materials such as cement and concrete, but you can also apply it to all other materials. You're able to do qualitative and quantitative predictions of phase assemblages occurring to a very complex reaction. Based on that, obviously, you get quite a lot of understanding. And finally, once you have a lot of understanding of these matter, you automatically reduce the experimental efforts in the lab, and especially in industry, that's also related or translated into costs. And finally, you can work relatively cost efficient and time efficient to come up with new ideas and to test these new ideas using thermodynamics. All theory is great. In order to do a really nice thermodynamic calculation, the first thing you really need to work on is a very complete data set. Because if you don't have a complete data set, you can do a lot of push-the-button calculations and it gives you some results, but these results don't necessarily mean that these are the right results. So in the Core Project 1, together with Barbara and Fred, we worked a lot on this database and working out this data set really for the cement hydrates. And at the moment, we're having it as a state that we can really apply this database for all sorts of thermodynamic calculations in the cement world. Just in May, we're going to have another workshop on the application of these tools at EMPA, and I think the registration is still open for people who are interested in that. And there we also introduce a new version of these data sets. Nevertheless, coming also now to a bit of the application part of these data set, I mean, one example that people may be familiar, and I think it's quite important also to an industrial scale, is understanding the phase assemblages of hydrated cement. And in the thesis that I did at that time in Core Project 1, I've chosen one example I found particularly interesting was the impact of carbonate or limestone on cement hydration. What we basically found is that even small amounts of limestone that you can add to your system, they can change the mineralogy a lot. I mean, just have a look at this phase diagram. I mean, just if you look here, if you're starting from 0 limestone to, I don't know, 10, 20%, you will change the phase assemblages quite dramatically. And what basically happens is if you're having a limestone blended cement, you would start to stabilize ettringite and monocarbonate, and you would not end up with the traditional phase assemblage composed of monosulfate that you would and ettringite that you would think of in an OPC, which is limestone. And that has also implications, of course, for other things such as space filling, total specific solid volume, and you can see here on that slide. And what we found basically is that if we really master this reactivity of alumina, and we know how much of the limestone can react, we can basically try to use these relations and optimize the cement with respect to maximum space filling. And you can see this here that, I mean, as a function of limestone content, the space filling will increase first and then decrease again. And this is a very nice thing because you can basically try to use these relations to optimize your cement for maximum space filling or minimum porosity. And then we went a step further with Duncan. At that time, he provided me a lot of data, and thanks to that, on research they had done at Aalborg Cement at that time, where they really looked into also the performance of these limestone blended cements as a function of available alumina, sulfate, and added calcium carbonate. And I was doing some complementary calculations, and we can see really nicely that there is apparently a correlation on the total porosity coming from the space filling to the strength that you would measure really in the lab. And I think this was a nice way how to demonstrate also that we can really apply these tools in industry. And I think in the last 6 years or so, we've seen also a lot more of these applications popping up. And we see now that there's multiple blends or ternary blends that are based on limestone and alumina-rich SEMs. They have great potential to really leverage these synergies in there. I mean, here's just one example I found in literature from fly ash system. There's an example also with Duncan and Karen. They're very active on these now, on the calcite clay limestone mixtures. And you can see really nicely by understanding these phase relations, you can see you can understand also why you have an optimum in performance at some point and why you don't have it in other systems. And I think this is a very nice way to show really that these thermodynamic calculations helped to understand these complex phase relations and can also be used as a base for smarter product design. And I think this was a nice learning. And seeing now also how the tools are being applied also in industry, I must speak for myself, it is something where you can learn a lot from. The next example is going a step further. I mean, in the meantime, I changed to Holcim, and I think in 2010 or so, we met for the first time and said we want to initiate this Transcend project. Karen quickly introduced this Transcend project. It's a very nice setup of about 15 PhD students. They all follow one aim. They just want to understand the basic interactions of water with concrete or cement paste. And we had the pleasure at Holcim to host an industrial doctorate. And we had a guy from Ecuador here. His name is Luis. And he's done an excellent job in investigating for us the impact of water activity on the volume stability of hydrates. And I think this is, again, a step forward because what we were doing, say, till 2011, 12, 13, we were mainly restricting our thermodynamic calculations to saturated conditions. But if you look to the environment, about 90% of the concrete is basically not exposed to water, but exposed to water vapor, such as we have in here now. And just here you see a graph from the temperature and humidity fluctuations from my hometown in Weimar. you can see that temperature will change a lot during the year, and even the humidity changes a lot during the year. So Lewis really should investigate what happens actually to the hydrates. I mean, how do they interact with these changing conditions? What he basically found is that you can group the hydrates in hydrates that are sensitive to water vapor and hydrates that are not sensitive to water vapors. Here you see some video where Lewis put some pellets of monosulfate and monocarbonate. He compacted them together, and then he exposed them from low humidities to high humidities. And you can clearly see that there's monosulfoluminate is absorbing quite a lot of water, expanding, and you see this cracking here, and it's nicely shown in this video here, whereas other phases, they basically don't change their hydration states. And I mean, this is a really nice, literally example to really show how these hydration change or hydrate state changes impact the stability. And finally, he's developed a set of methods, of simple methods and more sophisticated methods such as sorption calorimetry in collaboration with Lund, to really establish a nice thermodynamic data set that we can apply to basically quantify all these interactions that we have between cement hydrates and water vapor. And finally, we could derive phase diagrams that are shown here, like for monosulfoluminate water, and you can see as function of temperature and relative humidity, we can have different hydration states, which are all related to different specific solid volumes. And basically, now having that in the thermodynamic code, we can predict these volume changes. And this is, I think, a step forward, because I think it's very helpful also in the future if we extend these kind of studies to things like CSH, etc., to better understand shrinkage of cementitious materials. I mean, you can see this here now. I mean, based on this, we can really predict, say, specific solid volume changes as function of relative humidity. I mean, this is basically chosen on this very simple example on monosulfoluminate. But once we have done all the phases, we can also do it for a very complex set of materials. And I think this is, again, is a step forward in the thermodynamic method. So we can also now apply these tools to unsaturated conditions. And that hopefully really, as I said, provides us a link to understanding such phenomena like shrinkage, etc. The other thing is I'd like to show is a result that he has obtained on the thermodynamic stability of ettringite. Ettringite is a phase that got recently quite a lot of attention in applications such as calcium sulfoluminate cements. I mean, a lot of people have filed patents on these systems. And Louis also investigated the thermodynamic stability of ettringite as a function of relative humidity. I mean, we haven't yet finished the final calculations, but what we can clearly see based on sorption calorimetry and sorption balance measurement is that in the range between 65 to 100% relative humidity at 25 degrees C, ettringite is stable. Then there is a range from 5 to 65% where there's a bit of uncertainty, but I think if the system comes from saturated condition, we believe that ettringite is persistent, and at about 5% relative humidity, ettringite will finally decompose to meta-ettringite. And I think that, again, this is opens up for us a new field of understanding complex phase relations, and also helps us to optimize our systems further. Finally, I mean, continuing my journey a bit, as I said at the beginning, I talked a lot about small scale. But working in industry, we quickly figured out that the big scale is decisive. And this is the favorite toy of my eldest son. Okay, he has it a bit in a smaller scale, but nevertheless, I mean, this gives you just a feeling for the size in which in the industry we're working with. And therefore, in the last example, I really want to show you a bit more applied work that we were doing in collaboration with CTU Prague that we also met during Nanocem, where we did develop an easy-to-use software for our technical service people that is called Holz and Content, where we just predict the concrete temperature evolution, especially for mass concretes. And I mean, here again, you see a basic intrinsic property of the cement hydration, which is this calorimetric curve. And in principle, what we do see, there's a lot of debate going on how this curve should be, how can you basically relate the different peaks to the different phase evolution. But for the engineers, the real value is basically the area underneath. And this area underneath, you can easily nicely measure with a colorimetry and basically on a sample that's that big, you can derive very nice properties that are related to structures that are as big as the size of a dam here. And I mean, these tools, they were quite successful. I mean, and especially in an easy to use way, can be a nice translation of the basic thermodynamic fingerprint, which is an alpha pure reaction to application. I mean, to give you a scale how things are done in practice at the moment, I've chosen some data from Holz in Germany here. In 2008, they were constructing a big waterlock in Germany, and there they had a challenge to concrete a slab. It was about 200 meters long, 12 meters wide, and 3 meters thick. And the maximum adiabatic temperature in the core of a concrete should not exceed 56 degrees C. This is coming from a German standard. And basically, to show that your cement or concrete mix design works, you need to do a huge scale trial. I mean, this is in this standard, you have to do a 2 by 2 by 2 meter concrete cube. This is a bit bigger than the size that we know from the concrete labs, and it's also a bit more heavy. I mean, obviously, you have to move about 20 tons, and you do not want to do this experiment too often because, first of all, you don't know what to do with 20 tons of concrete all the time. It's tough to move it, and it's also a bit expensive. So with that tool, you could basically minimize these big scale trials to a small extent, and on top of that, it helps you also to really optimize your mixing. Based on these results from 2008, we got the experimental data, and we could use it obviously to run it as a benchmark case for our software. And you can see now, I mean, I'm not going into details with the software, but if we are employing all the boundary conditions that we had on site, and we got the colorimetry data from the quality control in Germany, that means we're having our kinetic model and our heat model. So basically, we could derive a very nice agreement between the experimental data and the measured data. I mean, and just now imagine that if you would have changed the concrete mix design, instead of going, say, with 290 kilograms of the SEN3B and 90 kilograms of fly ash, you would have gone with 350 kilograms of the same SEN3B that give you both equal strength, but in terms of temperature, suddenly you would be above the limit. So, and here you see, I mean, this is, again, a nice tool, a nice way how you can really apply thermodynamics in industrial scale and also together with people and customers and engineers that we work with to show that you can translate very basic chemical principles into practical application. Finally, I mean, you can then also obviously model the whole temperature simulation in the bottom slab, I mean, in real time, and you can see whether there are still some bottlenecks in the real structure. But all in all, I think, what I wanted to show is really that we can use really simple, not simple, but very complex fundamental mechanisms to really bring them into a large-scale applications. I think this is really what was the purpose of this talk today. I mean, first of all, to go with you to the journey that I also made during the last 10 years. I mean, starting off with a tough week in Aberdeen in 2004, but finishing off nicely now in industry. And I mean, there's challenging time ahead. I mean, for some of you who had read the news, we will certainly see some exciting developments in the next 10 years. I mean, I really want to close with a saying from a person who had nothing to do with cement. And this is Laszlo, and he works as a standards controller at Holz in Group Service. And we once took a course together on, I think, creating effective presentations or something on the management side. He once said, well, Thomas, I think I consider cement is rocket science. Just no, and he just said, look at the scale. I mean, we're getting this big mountains. How incredible is that? We put it in a small bag like this. We make this nice stuff out of it, and it's for an incredible price that is way too cheap to sell to our customers. And just think about the whole chain that's involved to make this happen. And therefore, I think he's right. And I think it's also good that some people from the outside see this. And I think, therefore, it's also very interesting that we have Nanocem here. And I think we should use these fundamental results that we also communicate to the exterior people who usually see cement as a gray matter to show them that there's more behind than just the gray material and that there's a lot behind it. Therefore, I like this statement so much. And yeah, as I said, I'm now at the end of the talk. I mean, obviously, I have to thank a lot of people. I just got a few pictures from Alex. We started with the people from Core Project 1. I mean, Fred, Donald from Aberdeen, Barbara helped a lot with gems, then Alice, Duncan, who were my industrial supervisors. At that time, Karen, who initiated the whole thing. Alex, special things to Alex. She always sent me reminders to not to miss a deadline, etc. I think she's done an amazing job to hold the whole group together. I mean, this is, I think, also something we should thank you. Wholesome, I have to thank Michael and Marcus. I mean, they had given me the freedom in the last 6 years to basically move a bit left and right and going from the application side still to the basic research. And we had a great team, or we have a great team in Holcim, which is small, family-like. And yeah, we had fun there. Holcim Germany, I have to thank for the data. And I think for them it was also interesting to see that you can really use this simple data and make a tool out of it. For Transcend, I have to thank Louis, has done a good job. Lars, who helped us in Lund. EC for funding, and finally Vit, I hope he's here also for helping us to set up this tool that I showed at the end. And finally, I'd like to thank you for your attention. I hope there's some question. I hope I brought you a bit the thermodynamics closer to your mind, and I hope I showed you some ways how you can apply this knowledge. Thank you.